A plastic bottle can become a t-shirt if the factory chain stays clean, dry, and tightly controlled from the first step. This is not a craft hack. It's a full industrial process. Sort, wash, flake, pellet, and spin into textile fiber.
Everything starts messy. Mixed plastics, labels, caps, and leftover liquid.
The enemy is contamination. Tiny traces of the wrong plastic, dirt, or moisture can ruin fiber quality downstream.
In this video, we follow PET from bale to shirt, step by step, showing the machines and the checks that make it possible.
Before automation even begins, humans remove obvious contaminants, because one wrong item can poison an entire batch.
We'll keep the visuals practical, real facilities, real physics, and real reasons each stage exists.
The goal is consistent recycled PET, rPET, that can be spun like virgin plastic, without surprises in strength or melt behavior.
PET is polyethylene terephthalate, a polymer that can be melted and reshaped, which is why bottles can become fibers. But melting PET safely depends on purity and dryness. Water and contaminants can break polymer chains and weaken the final fiber.
Not all plastics behave the same. PET must be separated from HDPE, PP, PVC, and films to keep the melt stable. PVC is especially dangerous. A small amount can degrade during processing and create defects that show up as weak spots in fiber.
Color matters too. Clear PET typically makes higher value fiber, while mixed colors limit what the recycled material can become.
Moisture control is non-negotiable. Dry PET processes cleanly. Wet PET degrades and loses strength. This is why recycling is more like manufacturing than disposal. Every batch is measured, tested, and adjusted. Plants track consistency, especially melt behavior, because fiber spinning demands predictable flow through tiny holes.
With the basics set, we enter the 5 core stages: sorting, washing, flaking, pelletizing, and fiber production. First, sorting. It's where value is created, because purity at the start prevents expensive failures at the end. Bales arrive from curbside bins and deposit systems, compressed for transport but still full of labels, caps, and leftover liquid.
A bale breaker tears the compressed block apart, spreading bottles into a single moving layer for the line to handle. Manual pre-sort removes the obvious threats: metal pieces, large paper, and objects that don't belong in plastics at all.
Eye screens separate small fragments from full containers, because machines downstream work best on predictable item sizes.
Near-infrared sensors read the plastic signature as each item passes at speed, identifying PET versus other polymers.
Air jets fire in milliseconds, knocking targeted items into the correct chute, while the rest continue forward.
Clear PET is often separated from colored PET, because color becomes a permanent tint in recycled resin.
Bottles with heavy food residue or strange materials may be rejected early, protecting the quality of the mainstream.
Mixed rigid plastics, like HDPE jugs, are diverted to their own recycling route, keeping PET feedstock clean.
Lightweight films and paper labels are lifted away with air classification, reducing floaters in the wash stage. Magnets and metal detectors catch steel and aluminium, because metal can damage shredder knives and extruder screws.
Operators watch the belt flow and adjust gates, because real waste streams change hour by hour.
A single wrong material can slip through, so the line uses multiple checks rather than trusting one machine.
The PET stream now looks cleaner, but it's still bottles with caps, rings, and labels, so the next step is washing.
Before washing, some facilities remove caps mechanically, but many rely on density separation after shredding. Bottles are fed into a crusher that breaks them into rough pieces, increasing surface area for cleaning.
The crusher's goal is uniform pieces without too much dust, because fines behave differently in water and filtration.
After crushing, the material moves by auger and belt into wet processing, where pumps and tanks take over. In the wet area, every surface is about control, flow rate, temperature, chemistry, and residence time.
Now the process shifts from identifying plastics to removing everything stuck on plastics: dirt, sugar, glue, and ink.
The wash system starts with a pre-rinse to remove loose dirt and leftover drink, preventing the hot wash from becoming sticky sludge.
As bottles are wetted, labels begin to loosen, and the material becomes easier to scrub clean.
Any remaining mixed items are more visible when wet, so operators can spot and remove the worst offenders.
The PE stream enters the main wash line, where hot water and agitation do the chemical work.
From here on, the line is less like sorting and more like a giant industrial dishwasher, designed for plastic, not plates.
Even small bits of paper can show up later as black specks in yarn, so the wash must be relentless. Quality is built by repetition. Rinse, scrub, separate, rinse again. Each cycle reducing contamination further.
The end of sorting is not perfection, but a controlled input that the wash system can finish.
When this stage is done correctly, the plant increases yield and reduces rejects later in extrusion and spinning.
Next, washing, where physics and chemistry take PET from dirty containers to clean, dry flake. Washing begins with pre-rinse. Remove sugars and loose dirt, so the hot wash can focus on glue and oils.
Hot wash uses heat and controlled chemistry to break label adhesives and loosen inks without damaging PET. Agitation matters. Tumbling and paddles force water into crevices, where contamination hides. Friction washers add mechanical scrubbing, stripping stubborn residue that chemistry alone can't remove. Now comes density separation. PET is denser than water, so it sinks while most caps and rings float. Floating polyolefins are skimmed away, leaving a purer PET fraction at the bottom of the tank.
This sink float step is a major purity upgrade, removing the materials that would melt differently in extrusion.
Multiple rinse stages follow to remove chemicals, because leftover alkali can cause problems in melting and odor.
Fine screens and hydrocyclones remove grit and glass, protecting downstream equipment from abrasion. Water is constantly filtered and treated, otherwise the wash line just moves dirt from plastic into sludge. Clean flakes must be dewatered, so centrifuges spin out water before thermal drying. A thermal dryer drives remaining moisture down to safe levels for storage and transport.
Odor control matters. Food residue can survive in tiny amounts, so advanced lines add extra wash or deodorization.
Throughout washing, operators track turbidity and pH to keep cleaning consistent across changing waste inputs. If water temperature drifts, glue can re-stick and contaminate flakes, so heating is tightly controlled.
At the end of washing, PET looks clean, but moisture is still the silent threat, so drying continues.
Dry flakes move through air separation to remove light paper fibers that escaped earlier stages. Quality teams pull samples, checking color, clarity, and remaining contamination under strong light.
Only when flakes meet spec do they proceed to the next stage: flake finishing and storage. This is where recycled PET becomes a manufacturing feedstock, measured, documented, and controlled.
Now we transition to flake processing, consistent particle size, and low contamination for reliable melting. The goal is clean, dry, uniform flake, because extrusion and spinning punish inconsistency immediately. Next, flake handling and final cleaning steps that prepare PET for pelletizing. Then we'll melt and filter the polymer, turning flakes into pellets with consistent flow. And after pellets, we finally enter the textile world: fiber spinning and fabric making.
After washing and drying, PET is officially flake, a common traded form graded by color, purity, and particle size.
Even now, metal detection continues, because a single fragment can damage an extruder screw or tear a filter screen.
Air classification removes ultralight residues, while screens remove fines that would melt and burn too quickly. Some plants use optical flake sorters, catching tiny colored specks or PVC bits that slipped through earlier. Clean flake is blended to average out variation, creating a consistent feed for pelletizing. Consistency is value. Stable inputs reduce shutdowns, reduce waste, and protect fiber quality. Samples are checked for moisture, ash content, and contamination under controlled lab conditions.
When flake passes spec, it moves into pre-drying, because PET must be extremely dry before melting. Drying uses desiccant air to pull moisture from within the polymer, not just the surface. Only after deep drying can flake be melted without chain damage, bubbling, or haze.
Now we enter pelletizing, extrusion, melt filtration, and cutting molten plastic into uniform pellets.
Pellets will become the stable currency of fiber making, easy to store, blend, and feed into spinning lines. Pelletizing starts with final drying, because even small moisture levels can degrade PET during melting.
Flake feeds into a heated extruder, where a rotating screw compresses, melts, and mixes the polymer.
Temperature zones are controlled along the barrel, keeping melt stable without burning or discoloration. As the melt forms, any trapped contaminants become serious, so filtration is the next protective wall. A screen changer forces molten PET through fine mesh, removing solids that survived washing. Melt filtration is where fiber-grade recycling earns its name. Clean melt means fewer weak spots in yarn.
Pressure sensors monitor the filter. Rising pressure signals clogging, prompting a screen swap. Some lines add vacuum degassing, pulling out volatiles and reducing odor in the final resin. When the melt is clean and stable, it flows to a die head for pellet formation.
An underwater pelletizer cuts strands into uniform pellets as water cools and carries them away.
Pellets are separated from water, then dried again, because storage moisture would hurt later spinning.
Uniform pellet size matters. Consistent feeding keeps spinning lines smooth and prevents surging. Pellets may be blended with a small fraction of virgin resin to reach consistent performance targets.
Quality checks focus on melt flow, color, and contamination, ensuring predictable behavior in spinning.
If viscosity is too low, fibers can break. If too high, the melt won't flow cleanly through spinnerets. Once pellets pass inspection, they move to silos that feed the fiber plant continuously.
Now the process shifts from recycling to textiles. We'll melt pellets again and spin them into filaments.
From that point onward, the plastic behaves like a raw material for fabric, drawn, crimped, and turned into yarn.
Fiber production begins with drying pellets again, because spinning demands ultra-low moisture.
Pellets melt and are pumped under pressure toward a spinneret, essentially a metal plate with micro holes. As molten PET exits those holes, it becomes continuous filaments, each thinner than a human hair. Cool air quenches the filaments, turning liquid polymer into solid fiber in a controlled fall. A light finish is applied to reduce static and friction, preventing filament breakage at high speeds. Next comes drawing. Rollers pull fibers faster than they are made, stretching and aligning polymer chains.
This alignment creates strength, turning soft extrudate into durable textile-grade filaments. Depending on the product, filaments can remain continuous for performance fabric or be cut into staple for tees. For t-shirts, staple fiber is common,
short lengths that behave more like cotton in spinning. Filaments gather into a thick tow bundle, then pass through crimping rollers to add waviness and loft. Crimp improves feel and processing, helping staple fibers lock together when spun into yarn. The tow is then cut into uniform lengths, forming fluffy staple fiber that can be baled. Bales are weighed and wrapped, ready for the next textile step, carding and yarn spinning. Carding aligns the staple fibers into a web, cleaning out remaining microdebris. Spinning twists the aligned fibers into yarn, balancing softness with strength for everyday wear. Yarn cones feed knitting machines, which loop yarn into jersey fabric, the classic t-shirt structure. Fabric finishing controls shrink and feel, using heat setting and softening without compromising durability. Cut and sew lines turn fabric into a shirt through cutting, stitching, and inspection.
The final check ensures seam strength, fabric consistency, and clean appearance, with no surprises from recycled inputs. At the end, the bottle has become clothing, proof that waste can be re-engineered into a stable industrial material.
To make a comfortable tee, producers often blend recycled polyester staple with cotton, balancing softness with durability.
Blend ratios are controlled by wayfeeders because consistent yarn requires consistent fiber input every minute.
Carding and combing reduce neps and align fibers, improving smoothness and reducing weak points in yarn.
Spinning adds twist. More twist adds strength, less twist adds softness. Factories tune this for the target fabric.
Yarn is tested for tensile strength and evenness, catching problems before thousands of shirts are made.
Knitting creates loops rather than a rigid weave, giving jersey its stretch and breathable drape.
During knitting, sensors detect broken yarn. Quick repairs prevent long defects running through the fabric.
After knitting, fabric is relaxed and stabilized to control shrink when the shirt is washed at home. Dyeing must be controlled because polyester takes dyes differently than cotton. Recipes are tuned for blended fabric.
Finishing adds hand feel, softening, heat setting, and surface smoothing, without adding heavy residues. Pattern cutting stacks fabric layers. Clean cuts reduce waste and keep seams aligned.
Sewing builds the garment. Shoulder seams, sleeves, side seams, then hem, checked at each station.
Final inspection looks for surface defects, pilling risk, and seam strength, ensuring recycled inputs meet expectations. Packaging avoids excessive plastics. Many lines use minimal wrapping while protecting the garment from dust.
When done right, recycled PET delivers a product that feels ordinary because the engineering was extraordinary.
Across the whole chain, quality control is constant. Contamination checks, moisture testing, and melt behavior monitoring. Fiber-grade recycled PET depends on filtration. Without it, tiny solids become weak spots that snap filaments at speed.
Moisture is the quiet killer. Too much water shortens polymer chains and lowers strength, so drying repeats again and again.
Wastewater is treated continuously because removing dirt from plastic creates a second problem: dirty water that must be cleaned.
Energy use matters. Modern plants recover heat and optimize pumps because washing and drying are power-hungry steps.
Recycling can reduce demand for virgin plastic, but it only works if collection systems deliver enough clean PET.
Color and design choices upstream affect recyclability downstream. Clear bottles and easy-release labels help the most. Textiles also face fiber shedding. The industry pushes better yarn construction and filtration to reduce microfibers in laundry.
The big message is simple. Recycling is not magic. It's engineering, with losses, costs, and strict controls.
When those controls hold, a low-value bottle becomes a stable raw material for fabric and clothing.
Sort, wash, flake, pellet, fiber. 5 verbs that describe an entire industrial ecosystem working in sequence.
And that's the journey. A bottle's second life, not as trash, but as a t-shirt you can wear every day.